Thank you. Immersive video, often referred to as VR video or 360 video, allows content creators to capture and deliver unique experiences. Social media sites have implemented immersive video into their platforms, making it widely accessible to consumers. But what of builders who seek to design their own unique experiences? Where do we begin? My name is Sean Przybyla. I'm a solutions architect with Amazon Web Services, and I'm joined here today by Chad Schmutzer, also a solutions architect focused on EC2 Spot. Today, we want to take you through a solution we've built specifically for immersive streaming. So without further ado, let's get started. If you have any questions throughout this webinar, please post them into the chat. We will be moderating that as we go and answering some of those questions towards the end of the webinar. So where are we seeing immersive experiences? As I'm sure most of us have seen, there 360 video or 180 video or general immersive experiences are all over the place. News events, like the attacks in Paris had candlelight vigils streamed live in 360 degrees all over the world, which added a unique storytelling component. On the sports side, we've seen immersive experiences streamed live and also video on demand from sporting events like the NBA, who partnered with NextVR, I believe. And we're seeing a ton of other applications outside of the entertainment space in realms like architecture. So design of buildings can benefit greatly from immersive experiences. Real estate, so if you're looking to sell your home, there's applications of immersive video as well as computer-generated VR experiences to enable potential buyers to see the facility without actually going to an open house. So we're seeing this everywhere. Personally, I'm really interested in the mental health and mindfulness aspect of immersive experiences. I like to spend my weekends sitting on a beach in VR, either streamed live to my headset or generated by my computer itself. It's a pretty good way to get out on the weekend without actually having to leave your home. So let's dive a little bit deeper into the variations of immersive experiences. In this diagram here, you can see there's a few different experiences ranging from flat video, which we're all probably familiar with. We watch it on our television sets, on our mobile devices, on our computer screens. And then as we move further in immersion to the right there, you can see a few other experiences. Augmented reality and virtual reality, while providing a higher degree of immersion, are generally less accessible because they require head-mount displays, controllers, or proprietary hardware or sometimes software to enable these experiences. Immersive video, on the other hand, has been really proliferated by consumer social media networks, as well as delivery of headsets like Google Cardboard, which attach directly to your mobile device. And because of this, we're seeing immersive video as an emerging medium for creators and delivery of content to mass consumers. Immersive video is the first VR quote-unquote experience for many audiences because of this. And I personally see it as a stepping stone to mass VR adoption through those other ancillary devices. So to summarize, immersive video is really the gateway, I think, because of its accessibility into the augmented reality and virtual reality platforms that we're starting to see today. It is relatively easy to produce, as we'll see through the demonstration later, or through the architecture later. But I think one of the challenges that remains to be solved for content creators is the distribution and monetization of immersive videos. So with that, let's dive right into the capture and distribution of an immersive video streaming solution. So if we imagine For instance, that we have a live sporting event. Maybe it's a football game, as is in the case of this diagram, or maybe it's a basketball game or any other live event that we want to capture and deliver to consumers. On one end of the system, we have that event, and on the other end, we have a plethora of devices that we want to deliver this event to. So how do we do that? Well, the first step is to capture it. And we do that with some type of camera array. So sensors that are capturing the frames of video. We might be editing and stitching as part of that capture process, and then delivering to another fleet of processing infrastructure. Now, the reason we separate the processing from the capture infrastructure is that generally, as part of the distribution of live content, we're going to be transcoding the original source content into multiple renditions to deliver to the end devices. And that transcoding process takes a significant amount of infrastructure that we generally don't want to bring, say, to a live event itself. We're capturing the live event, we're sending it to our processing infrastructure, we're sending it to our infrastructure to transcode, to repackage, to maybe even apply digital rights management to. And then in the final phase here, we're hosting that now processed content in our delivery infrastructure. So that would include our origin infrastructure, any type of caching we have to protect our origin. We might apply some authentication in this phase. And ultimately, our delivery infrastructure is going to carry the bits to those end devices. This is a pretty high-level description, but I think it's a pretty accurate one. So with that, we'll dig into each one of these sections as it pertains to immersive live streaming. So as previously mentioned, the first step is to capture. And so if you're looking to capture an immersive experience, you're going to end up probably picking up one of the cameras on the screen here or something very similar. So I just wanted to provide a couple of considerations to you while you set out to purchase one of these devices. There's a handful of considerations here ranging from number of sensors to onboard image stabilization. And all of these features here listed on the left are going to drastically increase the cost of the device. In the case of our reference architecture, we used the Insta360 Nano, as well as the Ricoh Theta S, which are two devices that would be at the kind of the entry level of the market. And those devices have some nice features in that they, for instance, connect to a mobile device and use the onboard battery of the mobile device. They also had an RTMP streaming capability, so we could capture and stream to our infrastructure all from our mobile phone. But not every camera has that. For instance, if you're building a custom array with GoPro devices, you may need to implement your own out-of-band stitching mechanism, which we'll get into here in a little bit. But that's just one example of how the various camera manufacturers, the various features of those cameras may impact the overall design of your system. One key consideration on the capture side is the monoscopic or stereoscopic capture devices. I'd say in general, the majority of 360 or 180 degree video on the internet today is monoscopic. And what that means is the camera is only using a single sensor or single recording per field of vision. I think it's popular because it's cost effective, but there is another option depending on the experience you're trying to stream to your end users, and that's stereoscopic. And you'd be familiar with stereoscopic if you've ever watched a 3D film, if you've ever used a ViewMaster, as is kind of represented here on the right, or any similar technologies. The stereoscopic images are not a new concept, as kind of shown here. The ViewMaster has been around since the 1900s, but using them for immersive live streaming over the internet is relatively new, and it has some great things. It provides the end user an awesome experience, but it comes at a great cost. So it basically doubles the distribution cost as well as the processing cost, because you're capturing multiple recordings per field of vision, one for each eye, basically. So something to keep in mind as you're designing these systems. One other thing to keep in mind, I alluded to earlier, is the stitching and projection mapping. One of the more common ways to take all these fields of vision and stitch them together is in what's called an equirectangular stitching or equirectangular projection. And an easy way to think of this is how we represent the Earth, which is obviously a sphere floating in space, onto a two-dimensional plane, aka a map. So you can see that while this representation is relatively accurate, and accurate enough, obviously, for us to use in everyday use, it does have some challenges. One is that as you get further and further away from the equator, you start to see deformation of the actual land masses. And another challenge with this mapping technique is that you have a lot of wasted data near the poles of the sphere. And these problems don't go away when we use the same mapping technique for 360-degree streaming. So if you imagine we're capturing the content with one of these with one of the aforementioned cameras, we're stitching either in the camera or out of band into equirectangular projection. But if we're using equirectangular to stitch the content together, we're still wasting data at the poles and having some degree of deformation as we get it further and further away from the equator. So there are other stitching and projection mapping techniques. The most widely used and I'd say supported by the ecosystem is equirectangular, just generally due to its simplicity. But if you're looking to optimize the delivery, or you're looking to optimize the quality, I would recommend investigating some of the other transformation techniques like cube mapping, pyramid mapping, and barrel mapping. Most of the implementations I've seen in the field with these technologies has been very much customized to the specific application. Whereas equirectangular, there is a decent ecosystem of players and transcoders and other components. So just know that if you look to optimize using cube mapping, pyramid mapping, and barrel mapping, you're going to be probably implementing a lot of that on your own, or working with a black box solution provider who provides each component to you. So what about audio? We talked a lot about the visual aspect, whether it's stereoscopic or monoscopic, as well as how many sensors and other things that are all visual aspects of our stream. What about the audio side of the equation? Well, one thing to keep in mind with the audio for a 360-degree experience that may not be obvious is that when a user is moving their head, or a user is changing the perspective on their laptop in the live stream or the 360-degree experience, you want the audio to reflect the changes in perspective that have been made. And there are a few techniques for doing this, but I think the most prolific one is the use of ambisonic audio. And again, ambisonic audio is not a new technique developed recently just for VR or immersive experiences. It's actually something that was developed in the United Kingdom in the 1970s. basically to provide a full sphere surround sound experience. And so what we're seeing in the field working with folks developing these solutions is that ambisonic audio integrated into the client experience and taking telemetry data from the headsets or taking telemetry data from the viewport, if you will, on the screen can be used in conjunction with ambisonic audio to adjust the perspective of the human ear as if your head was in the experience. And the way it works, just to summarize, is basically your sound hits the human ear at slightly different times. And by using things like spectral filtering, we can filter the sounds so that they sound slightly different, and therefore your ears pick them up differently as if they were often to the left, often to the right. And we can shape those filters as the user's head moves or the user's viewport moves through space. If you're doing this in a live situation, you can use spatial microphones. I think Sennheiser has one. And you can actually mux this live audio signal into your live broadcast along with the video. For video on demand or for file-based workflows, there are a couple workstations that allow you to edit ambisonic audio, much like you would edit stereo or surround sound audio. So now that we've talked about the capture side of the equation, we need to get it to our processing infrastructure. And we do this through a process called contribution. The biggest consideration here, or one of the biggest considerations here, is our bandwidth from that football game or from that event site to our infrastructure. In a traditional setting, this would be done through a satellite uplink and downlink to a broadcaster. In most settings now, this is traditionally done over an IP network and often done through just the public internet or the unmanaged internet. So just a couple of considerations. If you're streaming from your phone or you're streaming from one of the aforementioned devices, pay attention to the network you have. If you're on a Wi-Fi network at the event site, obviously there's going to be some challenges, potential challenges to uncover there. If you're using the public internet to transmit those bits, I would recommend, if possible, to use multiple ISPs out of an event site in case there are any challenges with the ISP. Also consider any latency latency challenges that you might have if you're, say, planning to stream in 360 some type of sporting event that has betting involved or something like that. Latency can be a huge consideration, in which case you would want to select a protocol and use a network that allows you to get the least latency possible. On the protocol side, I've listed a few common protocols here, along with some of their properties. RTMP, originally introduced by Adobe, has proliferated, I think, the ecosystem of transcoders and encoding hardware and camera devices. For instance, if you were to stream your live stream to Twitch, your gaming experience, you would probably be using RTMP to do so. RTMP is great in that it's integrated into a lot of pieces of software, but because it's an Adobe protocol that has technically been deprecated, the life cycle of that protocol is coming to an end. So what we're also seeing is folks pick up Apple HLS or HTTP live streaming, which is traditionally used for client distribution, not necessarily contribution into infrastructure. One of the challenges with HLS, however, is the latency it introduces due to the segmented nature of the protocol. which brings us to RTP, which is a relatively open protocol with relatively low latency. I would recommend whenever possible to use RTP with forward error correction. One of the challenges there, however, is it's not quite as prolific in the ecosystem of transcoders or encoders and packagers and origination systems. So just some considerations there on how we get that live stream from the event to our processing and distribution infrastructure. One quick note, I've alluded to a few times here. One of the obvious questions might be why do we need to send this feed from the event to our processing infrastructure? And the reason is that video today over the internet is transmitted over what's called an adaptive bitrate protocol or an adaptive bitrate mechanism. And what this really means is that we're taking that single source, we're taking that single feed from the event space, and we're transcoding it or transrating it into multiple bit rates or multiple versions. So in this case, we have 4K, HD, and SD. And the reason we do that is because we're trying to target all those devices which may have varying network connectivity available to them. And so what ABR allows us to do is give a suite or a bouquet of various bitrate resolution combinations to the client through a manifest, and allow the client to select the most applicable resolution or bitrate for that device and its network conditions. So that's what our processing infrastructure is doing, is taking in that single feed, transcoding to multiple bit rates. Which brings us to a few different options for processing on AWS. The architecture that we're diving into today uses Nginx in combination with FFmpeg. One of the design goals with this architecture was to allow folks to get up and started quickly and using general software from the AWS marketplace, as well as open source software. So Nginx in this case is serving as both a cache as well as an ingest server for our RTMP stream using the Nginx RTMP module. And FFmpeg is what's being used to transcode the source into those multiple resolution bit rates that we described earlier. But I want to make it clear that these aren't the only options for processing on AWS. There are a lot of different ways to do this. One is through our recently announced AWS Elemental Media Services. Media Live, for instance, could be used to transcode the live streams. Media Convert could be used to transcode file-based assets. And then we also have a wide partner ecosystem that includes Wowza and Bitmovin, as well as many others. So now that we've talked about the processing side of the equation, and we've transcoded our single source feed from the event site into our adaptive bitrate stack, we now need to dive into the delivery aspect, or how we get content from our origin infrastructure to the end devices. And there's a few considerations here. One is the resolution. To put things into perspective, to deliver a 4K experience in a 360-degree sphere, if you will, would actually take 12K worth of resolution because the viewport obviously is only looking at a certain angle within that sphere. So delivering 12K would take an immense amount of bandwidth to give that user a 4K experience. So there are some techniques like view adaptive streaming that have started popping up. The view dependent adaptive streaming basically adjusts the bitrate resolution with with awareness of where the user's head is pointed or where the viewport is in the sphere itself. I've seen this combined with pyramid mapping. So each plane on the pyramid is transmitting a different resolution based on where the user is looking. So that's one technique there to keep in mind. I would strongly recommend implementing a cache tier to protect the origin. This is just best practice for live streaming. Always use the CDN, another best practice for live streaming, as well as always using HTTP-based protocols when possible, when latency considerations don't impede that. And last, on the client side, the architecture we're releasing uses Mozilla's A-Frame. A-Frame is actually a web VR-based framework which allows you to build 3D scenes directly in your browser. We're just using it here in conjunction with hls.js to simply render a sphere, or as they call it, a video sphere, and project the video within that sphere. But A-Frame could be used, for instance, to integrate with a head mount display, to integrate with the control devices. It comes with a lot of native support for those capabilities. And so that was kind of a 50,000-foot view of the system. Now I just want to quickly go through the architecture that we've released on GitHub. And just to quickly summarize, we're taking a live source, again, imagine from an event or from some point of interest, from a capture device. In our case, the Insta360 Nano supported RTMP directly from the cell phone that it was attached to. We are streaming this to multiple origins hosted on EC2. And these origins were running Nginx RTMP, basically ingesting the content, transcoding the content, and serving it up for a client to request and view and play back. As I mentioned earlier, there is a cache fleet protecting those origins, so that if there is hundreds or thousands of clients requesting those feeds from the origination infrastructure, the cache fleet can dynamically and horizontally scale to protect and serve those requests. And CloudFront also provides another layer of caching, regional caching at the edge for those media segments. When the live event is done, or when the camera stops publishing, a video on demand asset is sent to S3. And this video on demand asset can be transcoded again by the encoding fleet, which is running FFmpeg, but potentially creating more renditions than is possible with than in real time. All the infrastructure you see here in orange, the EC2 instances, was deployed using EC2 Spot. So to talk a little bit about EC2 Spot, I want to hand the mic over to Chad Schmutzer.
Hey, thanks, Sean. All right, so when we built this reference architecture, we wanted to set out to make it as not only as cost-effective as possible, but also as scalable as possible. And so we chose to design this entire architecture to take advantage of EC2 Spot instances. So let me just dive into quickly what EC2 Spot instances are and how we adapted this architecture to take advantage of them. Right. So you're probably familiar with the first two consumption models for EC2, on-demand and reserved, where on-demand equals utility-based pricing, reserved equals reservation-based pricing. So the third model is the ability to essentially request access to spare EC2 capacity in our data centers, essentially enabling you to achieve significant discounts, often up to 90% off of the on-demand price. And when it comes to using Spot instances, there are really just a couple of rules to keep in mind, right? The first is that the price changes very infrequently based on supply and demand of that spare capacity, right? And the second rule is that You can simply just request the capacity. If we have it, we'll give it to you. You'll pay the current rate. If at any point we need the capacity back, we'll give you a 2-minute warning to wrap up your work, and we'll take the capacity back. And so, right, those are the very two simple rules. So given these two rules, let's understand how we can use Spot instances within this particular reference architecture to achieve the goal that we have, which is immersive streaming. So I've just told you Spot instances are spare EC2 capacity. Well, what are some tools that we can use or strategies that we can use to achieve the capacity and the scale, with keeping cost in mind? So we have an API called EC2 Spot Fleet. EC2 Spot Fleet is a single API call that lets you launch anywhere from 0 to thousands of Spot instances within a single call. You can tell it to diversify your resources automatically. You can allow it and have it scale up and scale down based on real-time requests coming in, with metrics that you choose. You can also apply custom weighting. So this allows you to create a balance across the different instance types that you're using within your Spot fleet. So a lot of power and capabilities within hand by using Spot Fleet. And this is going to be key within our architecture, and I'll explain why here. So as Sean mentioned, there are really 3 different components within the architecture where we're taking advantage of Spot instances, and I'll just kind of dive into each of these pieces. So the first is going to be the origin tier, right? So what we've done is we've set up a couple of origin servers, a primary and a backup, and these are locations where we're essentially enabling capture of the live source, right? So we've got a primary and a backup, right? This allows us, redundancy at multiple levels. We've got these deployed in separate availability zones. They're running on separate instances. This again, this allows multiple redundancy, both from a network and connectivity perspective as well. So what are some of the things that we took into consideration when we were designing the origin tier to run on Spot? So what we did was we set up 2 Spot fleets, one for the primary and one for the backup, and we simply said, let's make each of these a size 1, right? So what this means is we need a minimum of 1 instance in each of these, right? Because we have essentially 1 primary and 1 backup server at all times. And so what Spot Fleet will do is Spot Fleet will do its best to maintain a size of 1 for each of these Spot fleets, right? So what about network connectivity, right? So in the case that an instance is going to be interrupted, we need to make sure that the same IP address, the same network connectivity is in place if an instance needs to be replaced. So the way that we handled this was we configured and provisioned an elastic network interface within CloudFormation. And what we do is we take one elastic network interface for each of the origin servers, the primary and the backup, and we simply attach these network interfaces at boot in user data. So that means if an instance is going to be replaced, the new one would simply attach the same network interface that was in place for the one that it was replacing, right? Then we went along and assigned an elastic IP address and associated that to the elastic network interface. So this way, we always have the same public-facing IP address assigned to that network interface that's attached, to our primary and backup origin servers. And then finally, we have a process called a post-process script that continually runs on the origin servers that's pushing data up to S3. So as live streams come in, we record those streams, we save them, and then we copy them up into an S3 bucket for transcoding down the line in the transcoding tier. So the next tier is going to be the edge cache, right? And so the edge cache essentially consists of a single Spot fleet that has been designed to scale up and scale down based on the amount of network traffic coming to it through the load balancer, right? So we have a single Spot fleet comprised of multiple instances with application with auto scaling built into it, and then these instances are sitting behind an application load balancer for load balancing traffic across this entire Spot fleet. So what are some of the things that we took into consideration when we set up this edge cache tier? Right, so the first thing is, as I mentioned, it's a single spot fleet, but we've told it to use diversified for the allocation strategy. So what this means is we're telling, hey, spot fleet, diversify the instances within your fleet across as many availability zones as possible, across as many instance types as possible, in order to reduce any potential interruption that would affect our edge cache tier, right? So we're diversifying our resources across as many pools of capacity as possible. The second thing that we're doing is we're dynamically configuring the private IP address of the Elastic Network interface that we've attached to our primary and backup origin servers directly into the Nginx configuration, right? So we're using Nginx, and what we're doing is at boot time, we're telling Nginx, hey, here are the primary and backup origin private IP addresses that you can use to fail over to. So in the case of an interruption, Nginx can simply say, okay, I can flip back from the primary to the backup origin to continue receiving that live stream. We also automatically attach the instances within this spot fleet and the edge cache tier to our load balancer. We set a script on the instance that monitors for the 2-minute spot instance interruption notice. If that notice does appear, we catch it, we detach the instances from the load balancer and drain connections from the instances that are going to be detached. Here's an example of the script that's running on the edge cache instances, just looking for that spot instance interruption notice. If it does catch it, it simply calls, deregisters targets from the load balancer target group. So finally, the last tier in this case would be the transcoding tier. So you can think of the transcoding tier as a batch workload type environment, right? Where we're taking work that's being inputted into an SQS queue. We're doing some transcoding. If we have more transcoding to do, we can scale up the spot fleet that's powering the transcoding tier. If there's less work, we can scale it back down, right? So we're not spending any more money than we need to. So what are some things that we took into consideration here? We have a spot fleet that is, instead of being diversified, we've told it to just simply use the lowest price. This provides the most cost-effective tier for batch transcoding processing. Second thing is, every time a new stream has been recorded and uploaded to S3 from the origin servers, we tell S3, hey, create a new message in the message queue so that we know or there's some work to be done. And so then we run continuous jobs on the transcoding tier instances looking for work that's in the SQS queue. If we find messages in the queue, we check them out. We do the transcoding, and once the transcoding is complete, we copy the results back up to the S3 egress bucket for further processing or for viewing with video on demand capabilities. So that's really it. We're really excited about this architecture. We hope that you take some time and visit this link here on the screen. This will take you directly to the GitHub repo where you can check out the code. You can go through it, understand all the kind of rich features that are involved with it, and send us your pull requests or submit your questions directly into the GitHub repo, and we'd be happy to respond to you. So again, thank you for attending. We'll take a few minutes now to just look through the questions that came through the chat room and see what we can answer here for you live.